Hello everyone, my name is Anoop Cherian and today I'm presenting our NeurIPS datasets and benchmarks track paper titled Evaluating Large Vision and Language Models on Children's Mathematical Olympiads. As we all know, recent years have seen a significant progress in the general purpose problem solving abilities of large vision and language models such as ChatGPT, Gemini, etc. Some of these breakthroughs even seem to enable AI models to outperform human abilities in varied tasks that demand higher order cognitive skills. Begs a systematic analysis into where the AI stand with regards to human cognition. In this paper, we seek to find answers to the following questions. Namely, are the current large AI models indeed capable of generalized problem solving as humans do? How well do AI models perform on tasks that need broad skills? Do they transfer knowledge to solve new problems? And how effective are they in solving vision and language problems that even children can perform well on? We attempt to answer these questions from the perspective of comparing a well-trained AI model to the various stages in human cognitive development to understand any correlations between human and AI cognition. As we all know, humans develop their problem-solving abilities over a period of development towards adulthood, and the type and nature of problems that they can typically solve at different stages of their growth vary significantly. The cumulative knowledge gathering in building human intelligence enforces an order to the way cognitive foundations are established in rational agents. If we want artificial generalist models that think and reason like humans, we should expect these models to reliably demonstrate primitive concepts towards building up to reason about more complex problems. But the main question is, how do we do such comparative analysis? Is to compare human and AI performance on tasks that can be compared one-to-one on. One such task is the task of mathematical and algorithmic reasoning for solving mathematical Olympiad problems. A key challenge is to find a test that we could use for such a study. Only a handful of formal mathematical Olympiads with significant human participation tests children's mathematical aptitude from very young ages. One such Olympiad that we use in this study is the Mathematical Kangaroo Olympiad, which is a popular international competition targeted at children from grades 1 to 12. Each exam tests children's deeper mathematical abilities using puzzles that are appropriately gauged to their age and skills. This makes the problems from this Olympiad and the kids' performances on it directly comparable to the supposedly adult level performances that we expect from large language models. Using the puzzles from MK, we created a dataset called Smart 840. Our dataset consists of 840 problems from years 2020 to 2024 for grades 1 to 12. Math Kangaroo also has recorded the children's performances for each of these exams. These exams are of multiple choice type. Our key idea is to analyze large vision and language models' power on mathematical reasoning and compare their performances directly to that of children on the corresponding puzzles. In this slide, we summarize the data and children's participation statistics in the Smart 840 dataset. The figures A, B, and C show the distribution of participants over the years from the grades 1 to 12. As we can see in the plot C, the number of participants, that is the children participating in the Math Kangaroo exams, are about 40,000, and so thus we have a sample set size of 40,000 to compare against the performances of AI models on the corresponding puzzles. In the plots D, E, and F, we show the distribution of the various types of puzzles in the dataset. For example, the dataset consists of 4 categories of problems. In the categories of geometry, number, algebra, and logic. And as we can see, the distribution is almost even across the 4 categories. Further, some of the problems are text only while many others are image text. And we can see roughly 80 to 20% distribution of the puzzles between the image text and text only. Each of the problems in the Math Kangaroo Olympiad is categorized into 3 difficulty categories: easy, medium, and hard, and these are equally distributed as shown in the figure F. In the next few slides, I will give you a glimpse of some of the problems from the Smart 840 dataset. In this slide, the accuracy of correct responses of children in the respective grades against LVLM accuracies are reported on the Smart 840 dataset. Our results show that humans perform consistently between 55 and 65% across grades. However, interestingly, AI models have an entirely different and intriguing trend. They apparently find lower grader problems as difficult as higher grader problems. As you can see, for example, GPT-4o performance is 50.0 for grades 11 and 12, and it's 41.6 for grades 1 and 2, which suggests that the model finds higher graded problems as difficult as lower graded problems, which is counterintuitive to the way humans would solve such problems. In this plot, we compare the performance of LVLMs on subclasses of problems in our dataset, including their performances on geometry, numerics, algebra, and logic. We also plot the performances on image, text, and text-only problems. We find that on text-only problems, LVLMs do perform better than humans, but the performances are low on image text problems, suggesting that the lower performances are perhaps due to the inability of the LVLMs to understand and reason on images. Intriguingly, we also find that LVLMs perform substantially differently if they are asked to explain their solutions against if they are asked not to explain the solution but select the correct answer from the answer options without any reasoning. This radar plot shows the performance of LVLMs against humans, clearly showing the performances are substantially below that of humans in the various mathematical categories. We also find that the performance of LVLM do match with humans on text-only puzzles with an improving trend. Using the human performance data that we have, we computed various types of correlations between the hardness of the Smart 840 puzzles from a human perspective and whether the AI models also find those puzzles as equally difficult. We compute the difficulty index, discriminative index, correlations between the time taken by humans to solve the problems, the number of points attributed to a problem, and the distribution of the answer selections. We find that there are some weak correlations in some cases, example, the weight correlations here, and weaker correlations in difficulty indices. However, we have seen negative correlations with humans in other metrics, for example, the discriminative index or the entropy, as well as the time taken to solve problems. These negative correlations suggest that AI seldom finds problems difficult that are considered challenging for humans. This analysis suggests that they may have a different type of cognition and a different way of different core competencies. In the next 4 slides, I will present some sample responses of LVLMs on some of the problems that we have in the Smart 840 dataset. Using the human comparative data that we have from Mathematical Kangaroo, we compare the national rank and percentile of the LVLMs for MK Olympiad 2024. We see that current AI models are scoring very poorly compared to humans across grades, with their ranking in the 40s or higher for 1 and 2 grades, and in the 30s for grade 12. To conclude, our analysis using the proposed Smart 840 dataset reveals several intriguing results. We find that there is a lack of any significant correlation between the perceived complexity in solving puzzles by children and AI models. Instead, there are surprising negative correlations. There is a significant trend among LVLMs in performing low on younger grader problems and better at higher grades, which is counterintuitive. Further, while there is a substantial gap between the best of the LVLMs and the worst, and the gap between even the best LVLM and human adult level performance in reasoning is much greater. Our results suggest some ways that LVLMs, even the most advanced ones, may not really be reasoning in the ways that humans do. For humans, reasoning is an ability to think that goes beyond just similarity to training examples. But here we are seeing signs that similarity to the large mass of training examples appears to be what is driving performance across all levels of these problems. For people, the MK grade 1 and 2 problems are far easier than Olympiad style grade 11 and 12 problems. This suggests both that human reasoning is based on a different set of core competencies which the early grade problems test, and which a pure machine learning approach to training or reasoning is not really picking up on. Thank you so much for listening to me, and feel free to check out this website for updated details about our dataset, and please go through our paper for more details. Thank you.